So number 52 states, a car rounds a bank curve where the radius of curvature of the road is r, the banking angle is theta, and the coefficient of static friction is mu. A, determine the range of speeds the cars can have without slipping up or down on the road. So this one is tough just because of all of the variables involved. Let's first take the case where we're trying to figure out the maximum speed. The car here is represented by the blue block. Friction would act against the slide up the slope if it was going too fast. And we have the force of gravity and normal force. And the bank of the angle here is theta. So let's first go ahead and break those forces into their vertical and horizontal components. Just real quick on this one, theta down here is also equal to theta here. And in a moment here, it's also equal to this theta here, opposite interior angles, which means we can very quickly break these into their components. Remember again, the force of static friction, its maximum is equal to mu sub s times the normal force. We're going to assume it's at its maximum value. Based on that, then, we can now calculate what this term here would have to be. In this case, this vertical component here, because it's not accelerating vertically, has to be equal to this component downward here plus this component here. So force of gravity plus that component of the force of static friction acting downward. And I replaced F sub s here right away with mu sub s times normal force. Rearranging this to solve for the normal force, I'm first going to move that term to the other side, then factor out F sub n from both of those terms, and then solve for the normal force. So we know the normal force, this vector right here, has to be equal to the quantity we see here. So F sub n has to equal all of this. And you're like, well, wait, why do I need to know this? Well, we need that to be able to figure out the force of friction and everything else. So we're doing that first. Now let's take a look at the net force inward. If you take a look at that, we've got both this component acting inward along with this component acting inward. Together, these two are going to make my centripetal force. So the net force towards the center of the circle is the sum of those two. Once again, I've substituted mu sub s, F sub n in for the force of static friction on this one. And we can factor out the F sub n from both of these. Notice both of them have it. And here's where it gets a little exciting. Don't panic. I actually have an expression for F of n. Where right up above here, we already solved this one. So we can actually do this. We're going to substitute this whole quantity right here for F sub n, which gives us this rather hideous looking expression. Don't panic, it's all doable. Or rearranging just slightly, we can factor out the mg and get this expression. We're trying to figure out maximum speed at this point. Well, all right, so to do that, we can go ahead, and I'm just going to clean this up a little bit as we work so it's not quite so messy. We can now go ahead and set the centripetal force equal to that net force. Remember again, the net force here is another name for, this is net inward force, is another name for the centripetal force. So centripetal force, I'm going to take the mass of our car times centripetal acceleration. I'm using v squared over r in this case, equals this. Notice that I have mass on both sides of this, so I can cancel that out. Mass of the car is irrelevant. And rearranging it then, I get v squared equals r times g times that whole spiel. Or more precisely, taking the square root of this tells us our maximum possible velocity. Remember, we're going fast, we have a tendency to slide upwards, so the force of friction is going to act against that. This is the maximum speed we can go. Yes, it looks hideous because of all the variables, but you get the idea. This is half of the problem. We need to figure out also the minimum speed. So how do we do that? In a very similar process. If we're going too slow, we have a tendency to slide towards the center, but doing the same sort of thing we did last time, we can break those into their components. The normal force this time, in this case, what has to be true? This piece here plus this piece here, both acting upward, must equal to the force of gravity downward, mg. And rearranging that slightly to isolate the force normal, we can very quickly come up with this. Once again, over here, talking about the horizontal net force. In this case, notice that we get a difference here. This piece here is acting towards the center. This piece here is acting against it. So I'm going to subtract it. And again, I've replaced F sub S with this piece right here. Doing a little bit of manipulation on it, we can do that. Again, plugging in our normal force in here, we get that. And once again, we get this rather hideous expression. For those you remember, not much has changed. The only difference is before we had a positive sign here and a negative sign in the denominator. We just swapped signs. Doing the same trick we did before, we can very quickly, again, set centripetal force equal to this net force we have over here. That is the centripetal force. Mass cancels of the car, and rearranging it, we can get the minimum possible speed that you can go. It's the exact same expression again, but just with the positive and negative switched. So, answer to the part A, here's the minimum and maximum possible velocities. Part B asks, all right, given those expressions, what are the range of speeds possible if we've got this radius, this theta, and this mu? Fairly slippery conditions. All we're going to do here to figure out the minimum velocity is plug those numbers in. Radius is 100, g is 9.8, you could use 10, and theta is going to be 10 degrees and mu is 0.1. If you plug that all in and solve it, you'll get the minimum possible speed as 8.57. Likewise, we can do the same thing for maximum. Plugging in those numbers, you'll get 16.6. And those are our answers to this problem. That's the minimum possible speed, the maximum possible speed given those conditions.